All right, guys, we're going to start preparing for the Unit 6 exam with this worksheet. There is a quiz associated with this lesson, so be prepared for that. It's going to be on, for the most part, reaction types, but it could have some other things in it as well, such as balancing. So be prepared for things that were in the most recent lessons. All right, so what is the law of conservation? How do we show that mass and matter is conserved in reactions? What are the four main reaction types? What do Roman numerals have to do with writing formulas and naming? And those are your questions for the do now. So write those down and don't answer them yet, but those will be right after the aim. Those will be the first things in your classwork section of notes for the day. All right, mini lesson. What's the difference between an empirical and molecular formula? So empirical formulas are the smallest whole number ratio of elements in a compound, whereas the molecular formula is the actual ratio. We can do some pretty cool stuff with this concept. The first one is that we can determine the molecular formula by using an empirical formula. So here's an example. What's the molecular formula of a compound that has a molecular mass of 54, and the empirical formula is C2H3? So the first step that I recommend is to find the mass of the empirical formula. So as you can see, the mass of the empirical formula C2H3 is going to be 27 AMU. I just took the mass of a carbon and the mass of a hydrogen and multiplied by the number of each. The second step is to figure out how big this is compared to this, which is the molecular mass of the real molecule. So I'm going to do 54 divided by 27. To get 2. So 2 means that the molecule, or this guy, is 2 times larger than the empirical subunit, which is 27. So what I'll use is this number to figure out how big the molecule is, and I'll just take these subscripts and I'll multiply them each by this number, which gives me the molecule's formula as being C4H6. And as you can see, we have just solved the problem, so this is already done. And I was supposed to be writing the steps for A, B, and C above, so I wrote them here. All right, so let's talk about the charges that any of these elements in these particular groups might have. So if you're in group 1, you're likely to lose an electron and have a charge of positive 1. Group 2 would be positive 2. Group 13, positive 3. And group 14 could either be negative 4 or positive 4. And that's because in group 14, you have 4 valence electrons, and therefore you could go either way. If you were in group 15, you would have a charge of negative 3. Group 16 would be negative 2, 17 negative 1, and group 18 would have no ionic charge, so I'm just going to say Na. All right, now the next question, let's say we have a metal, M, that forms an oxide compound with the general formula M2O. In which group on the periodic table could M be found? So it sounds like you don't have a lot of information, but if we cross the charges, or I guess I should say uncross the subscripts to find the charges, then we would find that the charges would have been, on element M, it would have been this sort of invisible 1 down here, so it would be positive 1. And on the oxygen, it's no surprise that this 2 would be coming up and being a negative 2 on the oxygen. Oxygen's always negative 2, so we don't really need to worry about that. But they want to know which group on the periodic table could element M be found. So element M has a charge of positive 1, which means that it must be in group 1. All right, how do we show the charge of any element in groups 3 up to the metalloids? So what I just described here was the transition metals, which is why we would be able to show their charges using Roman numerals. So let's do the formula for copper 2 iodide. As you can see, we already have Roman numerals, which is giving me the charge for that copper. So this is copper with a positive 2 charge. And it's iodide, and iodide is the negative ion of iodine, which is in group 17, which also means its charge is negative 1. So let me cross those charges, and I'll get a subscript of 2 for the iodine and a subscript of 1 for the copper, which means that my formula is going to be Cu(I)2. If we want to find the charge of a polyatomic ion, then let's keep it simple. Look on table E. Let's use that strategy here in number 9. What's the formula of lithium carbonate? So lithium is in group 1, and its charge would be positive 1. Carbonate is on table E. Its formula is CO3, and its charge is 2-. Let's go ahead and cross these charges. And you'll get a 2 for the lithium and a 1 for the carbonate, which is why the final formula will be Li2CO3. So when we name ionic compounds, you should simply name the positive ion, name the negative ion, and if the metal is a transition metal, then you should include a Roman numeral. If you happen to have a polyatomic ion, then just give the straight up name of the polyatomic ion. Let's put this to work in a couple of examples. What is the name of NiBr2? So if you name the positive ion, it's going to be nickel. And nickel is a transition metal, so its charge varies, and we'll need to find it using subscripts. So the 2 on the bromine is telling me that the charge on the nickel must be 2, which is why the kind of nickel we're using must be nickel 2. And you just name the negative ion by writing its name, but you end it in IDE. So nickel 2 bromide is my answer. For Na2SO4, we're just going to name the first one, which is sodium. Sodium's in group 1, so it doesn't get a Roman numeral. You only get Roman numerals if you're groups 3 to 12. And SO4 is on table E, and I just looked it up, and its name is sulfate, which is why that formula is called sodium sulfate. If we want to name a molecular compound or a covalent compound, then you need to use prefixes to indicate the number of atoms of each element. Additionally, you would just write the positive nonmetal atom first and the negative nonmetal atom second. And you would also end the negative nonmetal atom with the ending "ide." Those geometric prefixes are here. But we would never use the prefix mono on the positive nonmetal atom. Let's make some corrections to the following misnamed compounds. Sulfur hexaiodide would be properly named sulfur hexaiodide. That's because when you are going to be using a prefix that ends in an A or an O, like hexa, and you're using it with an element that starts with a vowel, then you would drop the final A or O. So instead of hexaiodide, it's just going to be hex iodide. All right, so for dinitrogen monoxide, what I would say is that no capitals, please, and you would just say dinitrogen monoxide, again, dropping this final A or O before an element that begins in a vowel. You will never need Roman numerals to name molecules because the Roman numerals are for transition metals and molecules contain only nonmetals. All right, now when we balance equations, I recommend first making an inventory, and then second, start changing coefficients in the equation and updating your inventory until all elements are balanced. Let's put some of that to good use. I'm going to start with an inventory. So right now I see that we're missing an iron on the right-hand side, and we're also missing 2 oxygens on the right-hand side. Messing with the iron right now isn't going to be my first choice because I could put a 2 in front of the iron and it wouldn't help with the oxygen. So I'm going to start with oxygen, and I need to basically double the amount of oxygen on the right, as you can see. So I'm going to go up here to the oxygen-containing molecule CO2, and I'm going to put a 2 in front of it. And that's going to give me a total of 2 carbons and 4 oxygens. So I was able to balance my oxygen, but I did mess with the carbon. So now I have 1 carbon where I used to be balanced, and now it's not enough. So I'm going to add another 2 in front of the CO, and that's going to give me 2 carbons and 5 oxygens. So as you can see, things are starting to look a little bit dicey. When I change the carbon to try to make the carbon balance, the oxygen changes, and then everything has been undone. So in a case like this, what I suggest is to try something unconventional. For instance, what would happen if we tripled the CO2 and tripled the carbon monoxide? We would be able to update the amount of carbon to being 3 on the right. The oxygen would be 6 on the right. On the left, the carbon would be 3, and the oxygen would also be 6. And that's because you're going to be getting 3 here and 3 there. So just by changing both of those 2's to a 3 and doing something sort of unconventional, I was able to balance both the carbon and the oxygen. And in the last step, I would just need to finish up with the iron. I need to double that iron so that I can have 2 on the right-hand side. All right, so why should you look for polyatomic ions in reaction equations? It's because if the polyatomic ion is preserved from the reactants to the products, then you can list it separately and balance it as if it were an element. So let's use an example right now. I'll start an inventory and I will preserve polyatomic ions when possible. So I've done that here. I was able to keep the nitrate because I saw it here and here, but I had to list everything else separately. So I'll point out that for the oxygens down here, I did not count oxygens that were inside nitrates. I only counted oxygens that were outside nitrates. But this is my inventory, and one of the things that I can see needs to happen is that I need to balance the nitrate, the oxygen, and the hydrogen. I would say the nitrate is just as it's a good a place as any to start. So let me change the nitrate so that I have 2 nitrates on the left-hand side. So I did that and updated my inventory. That gave me 4 hydrogens and 2 nitrates on the left. So now I still need to balance the oxygen on the right and the hydrogen on the right. So I need to basically get 1 more oxygen and 2 more hydrogens. The easiest way to do that is just to double the water on the right-hand side, and then you'll have a total of 4 hydrogens, and at least outside the nitrates, you'll have a total of 2 oxygens. And from there, you can see that the equation has been balanced. So after all that balancing, I would just say that what makes it possible to identify missing reactants, products, and mass is the law of conservation. And in general, you can think of identifying the missing reactants and products in 3 steps. If we're trying to identify these missing reactants, what we need to do is make an inventory, and then we need to see which elements are missing on the sides of the equation. And then lastly, we need to think what compounds contain those elements in those ratios. And the steps involved in identifying the mass of a reactant or product are a little bit different. You need to set up a simple algebraic equation to show that the mass is being conserved on the left and the right-hand side of the reaction equation. And then you need to solve, and that's it. Let's do a correct numerical setup for calculating the molecular mass of glucose. So if we're going to calculate the molecular mass of glucose, you simply need to write down the elements, their quantities, and multiply them by their masses. So in the case of carbon, we have a mass of 12, but there are 6 of them. And I'm going to add that to the mass of hydrogen, which is 1, but there are 12 of them, and add that to the mass of oxygen, which is 16, but there are 6 of them. 12 by 16 is 72, 1 by 12 is 12, and 16 by 6 is 96. So when you total this all up, I believe you get 180 grams per mole. This is a unit that you might learn more about later, but for now you could say AMU, and I don't think anybody would be confused there. That's atomic mass units, but it's the same answer for both. All right, so lastly, I just want to make sure that you guys copy down these 2 pair-up questions and this summary question, which we will solve in class tomorrow. So thank you very much for listening, and I hope that you feel prepared for your exam. But for now, good night and good luck.